Welcome to the tutorial on vapor pressure lowering. We talked about this a little bit in class, and now we're going to continue to talk about it in a little bit more complicated scenario. So first of all, vapor pressure lowering is a colligative property of a solution. A colligative property is something that depends only on the number of solute particles and not on the nature of the solute particle itself. And here is an example of a colligative property of solution. Vapor pressure lowering. So when we take a pure solvent and we put a solute in that, we dilute that solvent a little bit, changing its mole fraction. When it's pure, the mole fraction would be 1, and when we dilute it, we take that mole fraction, we reduce it slightly, and then we could calculate that by identifying the amount of moles of each item. But when we dilute that, we reduce the vapor pressure. We reduce the number of molecules that enter the vapor phase. As we dilute that more and more, we dilute the vapor pressure more and more. We reduce the vapor pressure more and more. So here's the equation by which this vapor pressure is reduced. The vapor pressure is reduced by the amount of mole fraction times the vapor pressure when the solvent is pure, or when the component is pure. And this is known as Raoult's law. So we talked about this in class. We did an example in class. Now I want to take it a step further. All right, let's talk about the scenario when we have different types of solutes. Sometimes we can have a volatile solute, and sometimes we can have a non-volatile solute. So an example of a volatile solute might be something like methanol, an alcohol in water. An example of a non-volatile solute would be something like sucrose. All right, one of these will give off vapor molecules to the vapor pressure. One of these won't. All right, so how does this impact the vapor pressure of the solution? Well, only the volatile components of a system will contribute to the vapor pressure. So when we calculate the vapor pressure of the solution, we only have to worry about the volatile components. And we're going to sum those together. We're going to sum up all the volatile components, vapor pressures. So let's just keep it to two component systems, a solvent and a solute. So let's pretend that the solute is non-volatile. Then, if we want to calculate the vapor pressure of the solution, all we have to do is find the vapor pressure of the solvent. And that's going to be equal to the mole fraction of the solvent times its vapor pressure when it's pure, which is basically the equation we saw on the previous slide. On the other hand, though, we could have a system composed of a volatile solute and a volatile solvent. We're going to assume the solvent in this case is always volatile. So if our solute is volatile, then when we go to calculate the vapor pressure of the solution, we have to add the vapor pressure of the solvent and the vapor pressure of the solute. All right, on the next slide, I'm going to show you what that is going to look like. So in the simplest scenario, we just have to worry about a one component in our solution. And in a more complicated scenario, we have to worry about two components in our solution, both the solvent and the solute. Here's what that's going to look like in a graphical form. All right, this is two volatile compounds. All right, so we have a volatile solute and a volatile solvent. And here we've got benzene and toluene. The mole fraction is showing us the mole fraction of benzene. When benzene is pure, it means it has a mole fraction of 1. It has a vapor pressure of around 800 millimeters of mercury. However, when the toluene is pure, meaning the benzene has a mole fraction of 0, when the toluene is pure, it has it has a vapor pressure of about 300 millimeters of mercury. So those are the values when it's pure. All right, so pure A, if we call A the benzene, would be about 800. Pure B, if we call B the toluene, would be about 300. So if we want to calculate the vapor pressure of the mixture at any point along this line, we have to add the vapor pressure of the toluene and the vapor pressure of the benzene. So P total is going to be P toluene plus the P benzene, and that's just going to, we're going to import these equations into this total equation. We find that the total pressure of the solution is going to be the sum of the two partial pressures. Mole fraction of A times the pure A plus mole fraction of B times pure B. And this again is going to describe an ideal solution. And what we mean by ideal is that the solution fits our equations. Okay? And I'll show you some graphs of non-ideal solutions here after a bit. But let's do an example of this. Let's take pure methanol at 25 degrees Celsius, which has a vapor pressure of 100 torr, and pure propanol, which has a vapor pressure at 25 degrees Celsius of 37.6 torr. And let's mix these two. All right. If we take 800 grams of each solution, mix it, what would be our vapor pressure of our solution if it was an ideal solution? So we want to find the total pressure by adding these two partial pressures. So first, let's find the vapor pressure of the ethanol, and then we're going to add the vapor pressure of the propanol to that. Again, this is the ethanol, C2H5OH, that's ethanol. This is the propanol, the C3H7OH. Alright, so our problem solving strategy here is we need to find the mole fraction of each of these. Okay? Because this is going to be the mole fraction of the ethanol times the vapor pressure of the pure ethanol. And this is going to be the mole fraction, sorry, made a little mistake there. This is going to be the mole fraction of the propanol times the vapor pressure, pure, of the propanol. So we are already given these pure values. They're up here, given to us in the equation. So our goal is to find the mole fraction. Remember, mole fraction is moles of component divided by total moles of solution. So we need to find moles. How do we find moles? We're given 800 grams of each. And so we're going to take these gram values and we're going to convert them to moles. Alright, so if I have 800 grams of the ethanol, then I'm going to change that to moles by dividing by its molar mass. I just so happen to have the molar mass of ethanol here that I've already calculated. It's 2 carbons, 5 hydrogens, an oxygen, and another hydrogen. That's 46.1. And we're going to plug that into our calculators. 800 divided by 46.1. We're going to find that 17.35 moles of ethanol. And we'll do the same thing for the propanol. 800 grams of propanol. We're going to divide that by the molar mass of propanol. Molar mass of propanol I've already calculated. It's about 60.1 grams. And we're going to find that gives us 13.31 moles of propanol. Okay, so we've got our mole amounts. Now we can find our mole fractions. Mole fraction of ethanol is the moles of ethanol divided by the total moles in the solution, which is the sum of the ethanol and the propanol. And I get a value of 0.566 mole fraction. All your mole fraction values should be less than 1. And we do the same thing for propanol. The moles of propanol over the total moles of the solution. And this value is 0.434. Alright, you should make a notice right now, since we have a 2-component solution, our mole fractions, the 0.434 and the 0.566, would sum together to be 1. So I actually could have just subtracted, once I found one of them, I could have subtracted it from 1 and had the other. But I wanted to show you the calculation here. So now we just find those individual vapor pressures. We're plugging into this equation up here, the mole fraction of the ethanol times the pure ethanol. The pure ethanol was given to us in the problem as 100 torr. So 0.566 times 100 is 56.6. And for the propanol, we have the 0.434 mole fraction times its value when it was pure. The propanol is pure, 37.6 torr. So the vapor pressure to the solution from the propanol ends up being 16.3. And so when we add these two together, we have the solution vapor pressure, 56.6 plus the 16.3, is 72.9 torr. So that would be the vapor pressure of the solution when these are mixed. So we find the mole fractions, multiply the mole fractions by the values when pure, then add them together. And this is how you do a solution that has a volatile component as the solute. All right, I want to talk about that equation allows us to solve for an ideal solution. So I want to quickly mention what a non-ideal solution is. All right, so an ideal solution predicts the black line here when we add PA plus PB for a solution. But what we have is sometimes we have deviations from Raoult's law when solutions don't mix ideally. And so here we see a positive deviation, all right, because the actual exhibited partial pressure is higher than this straight line that we expect from the ideal solution. All right, and these positive deviations result from intermolecular force attractions. All right, these positive deviations result because when we mix the components A and B, they don't attract each other as much as when they are by themselves. So the intermolecular forces of A by itself or B by itself are stronger, greater than the intermolecular forces of A towards B. We can also see a negative deviation. All right, and here we have an example of the negative deviation. So our actual vapor pressure exhibited is less than the ideal vapor pressure expected from Raoult's law. And this negative deviation is brought upon from the exact opposite reason as the positive deviation. So now the intermolecular force attractions from molecule A towards molecule B are greater than the intermolecular force attractions of molecule A just by itself or molecule B just by itself. So A and B like each other more here, so they're less likely to enter the vapor phase. A and B don't like each other here, and so they're more likely to enter the vapor phase, creating higher vapor pressure. One last thing that you might see in another course where you do some fractional distillation, perhaps in an organic chemistry course. Fractional distillation is where we can purify a component of a mixture by slowly vaporizing that and recondensing and vaporizing over and over using a fractionation distillation column. And we can purify one component, the component that has the higher vapor pressure, by doing this. And this is because in a solution, the vapor pressures of these two components of the solution are different. So that's the principle behind fractional distillation.